Okay, I'm going to talk right now. I'm going to talk about NHDPlus extensions, and the main thing. Let me put my objectives up, and I'll go from there. The objectives are to understand our stream flow, volume, and velocity methods, and the data that goes with it, and then the supporting data. And let me mention two things right off. In NHDPlus land, an extension means data that's processed after all the core processing is done. So that's NHDPlus land speak. That's why they're called extensions. The second thing is flow volume velocity and the supporting data is all tuned or calibrated and harmonized to the period of 1971 to 2000. And sometimes I forget to make that point. I just want to make that point up front. So we're going to go through how we do the flow methods and the supporting data. Now, I'll first go through how the data is organized for extensions. Then I'll talk about the EROM extension, which is our main flow estimation method. And then we have another secondary method called the Vogel Flow Method. And then VPUAttribute extensions, which is all of the supporting data that was used in developing the flow estimates, and then plus some other data that has been developed lately. And then what is in the data tables, how the fields are used, and I'll also talk about how we estimate velocity. Okay, we have two methods for flow estimation. We have what's called the EROM, Enhanced Runoff Method. It's a five-step process-based method. That's the primary method used for flow estimations. We do mean annual and mean monthly. We also do the Vogel method, which is named after Professor Richard Vogel at Tufts University. You can find the reference to his work on that in the NHDPlus user guide. And then the supporting data for doing these flow estimations is found in a place called the VPUAttributeExtensions. Okay, now the extensions, they are organized by the vector processing units, the VPUs. For instance, the Tennessee River Basin would be MS06, and the EROM extension is in its own folder, and then the Vogel extension is in another folder, and the VPUAttribute data is in another folder. Now, the EROM flow estimation, it's a five-step process, okay? And there is also a separate QA module that we've developed that's incorporated, and it produces flow QA statistics and data tables that can help users do their own QA. And again, like I said, all the data is harmonized to the 1971 to 2000 time period. We use USGS flow gauges for adjustments and the QA, and the gauge data has to meet certain specific criteria, and I'll cover that in a bit. We do mean annual flow, and we also do mean monthly flow with the EROM method. There's 5 steps. Now I'm lettering them A through E, and that's because in the data table, the flows are lettered rather than numbers. So you have Q_E or Q_A rather than 1 through 5. Okay, now, so EROM, it has the 5 steps. Now, the first step is runoff. And this is, the runoff is process-based. It's a method that was developed by Dave Wallach and Greg McCabe of USGS. They do a runoff model, and the model is run on a monthly time step. And then what we've done, or what they've done for us, is they've taken 30 years worth of monthly data, and they've either aggregated it into a mean annual grid or into mean monthly grids for us. So step A is just taking the runoff data and accumulating it. And this is what the runoff map would look like. This would be for mean annual flow. This is our runoff. This would be how runoff looks in our grid. And it's a fairly fine grid that we're using, about 900-meter grid, I believe. The second step, step B, is called excess evapotranspiration. And this is something that, frankly, sometimes really works well, sometimes not. It has some scale issues sometimes, but a lot of times it improves things. Now, evapotranspiration is a huge component in terms of the water balance. Losses from evapotranspiration can be enormous. And this is an example graphic. This shows the Colorado River, where the dotted line would be where you simply just did a cumulative routing of your flows downstream. The solid line is taking excess evapotranspiration into effect. Streams will lose water as they go downstream. I mean, that happens, and even out east where I live in Virginia, we'll have cases in the summer where the stream will just lose water because it evaporates faster than it's coming back in. And it happens a lot in the west, and they'll just dry up a lot of times. So this is the solid line is with excess evapotranspiration, step B, taken into account. These diamonds are the observed gauge data, and you can see that it does pretty well until actually it gets here, and you've got one of those giant sucking sounds in the Colorado River where someone's pulling water out. This is where, for instance, plus flow AR would come to the rescue. The plus flow AR tables I talked about, these would come to the rescue in that situation. Other than that, if it's not there, the gauge data, which we also use, will come to the rescue there. Okay, now the next step is something we added because we were finding certain phenomenon in different river basins where, especially when we were using runoff, is sort of like the heart. Step A is the heart of the whole EROM method. And we were finding there were places where we were getting kind of a consistent bias. It could be for different reasons, and it was because, you know, the runoff model can't take everything into account, and there could be regional issues. It could be a persistent groundwater effect, maybe around the Great Lakes, that just could not be taken into account with a water balance model. But if we used reference gauges, which reference gauges are stream gauges that are minimally impacted by human activities, and if we did a regression of what the EROM flows were coming out of step B versus what the gauge flows were, we could do doing a log-log regression. We could adjust the flows, and this shows an example. This is from our QA work and from the QA data that is collected for EROM. The blue lines are from the step A runoff, and then the purple squares are after doing the reference gauge regression. And the red line is a line of perfect agreement between what the gauge flow would be on the x-axis and the EROM flow is on the y-axis. And you can see there was, with the runoff, a bit of a sort of consistent, persistent underestimation of the flow, and then doing the reference gauge regression, it did a good job, effectively took into account whatever the processes were. So it helps out in a lot of cases in terms of our flow estimate, and our whole objective is to do as good as we can with flows. Now the fourth step is the plus flow AR. And plus flow AR this is what I was talking about before, about where you can transfer water from one place to another place, or augment flows somewhere, or withdraw flows from somewhere, move them with the plus flow AR tables. And the fourth step in the EROM is to do the plus flow AR work, is to specify, okay, I'm going to take out 186 CFS from this point, or I'm going to put in 100 CFS here based on whatever the plus flow AR table tells me to do. So that's the fourth step. Now the fifth step is where we do gauge adjustments. And let's say there's a gauge down at this point on the flow line. What we do is we'll adjust upstream from that gauge, and we'll look up to where we're within 50% of the drainage area of that gauge, and we'll apportion our adjustments upstream. And then once we've made the adjustment here to match the gauge in our step E flows, that adjustment carries on downstream, and so it works its way down the system, doing the gauge adjusting as it works its way down the system. So the last flow estimate with the gauge is adjusted is should be considered your best flow estimate for EROM, because it's matching the gauges. Now there are two criteria. There's two important screening criteria that are used in what gauges and gauge flows we used. Again, remember I said 1971 to 2000 is our time period. The first is that we have to have at least 10 years of complete record for between 1971 and 2000. So, and if it's mean annual, that means we need at least 10 complete years of record to be able to use the flow. Mean monthly, it would be at least 10 years of complete record for that month. Now, the second criteria is NHD, the NHDPlus drainage area at that point needs to match up with the gauge drainage area within 10%. NWIS, where the gauges live, publishes a drainage area, and a lot of times those drainage areas are missing, in which case we're not going to use them. But if they're in there and we have our calculated NHDPlus drainage area, if they're off by 10%, there's something mismatched there, and I don't want to use that gauge for making my adjustments. Not sure what the mismatch is, but unless we can be in agreement that we're measuring apples and apples with that gauge, then, unless it can be an apples to apples comparison, I won't use it. So those are the two criteria that we use for our gauges. Okay, now this is what the EROM results file looks like. This is attributes of the EROM, mean annual EROM _ MA 0001. And as Cindy mentioned, when we originally started this, we thought we might have multiple types of flavors of our flows. So the 001 could be 0002 or 0197, God help us, but who knows. And the MA, it can also be 01 for January, et cetera. And then we have COM ID, the Q0001A, again, that's flow A. We keep all 5 flows in the file. And then we also keep the velocity estimates. Flows are in cubic feet per second, velocities are in feet per second. So for each of the 5 flows, and we retain all of them, we estimate we have the flow estimate and the velocity estimate. And for a given gauge along here, again, we'll have all 5 flow and velocity estimates. Generally, your best natural flow, quote unquote, would probably be Q001C after the reference gauge regression adjustment. And your best actual flow, your best flow estimate absolutely should be Q0001E, because that takes into account the gauge adjusting. And this one, for instance, this gauge is kind of interesting. This line flow is interesting. It starts out at about 808 CFS, and it gradually, with each step, you'll notice with the reference gauge regression, it's dropped it down to 765 CFS. Ultimately, this gauge is actually, this flow line, the COM ID is actually on a gauge, and it's, the gauge flow is actually 730 CFS. So it started out at 808, and the different steps kept knocking it down to what we would consider truth to be is 730 CFS. So that's the effect of the 5-step process that we run through. Now, I mentioned we also do QA, and we have a QA report that's produced for EROM for each VPU that's run. There's for each VPU, we have the EROM results files, and then we have an EROM QA report, which is a PDF, and then we have EROM QA files. This is what the QA report looks like. It gives you some summary of the data used. It gives you the number of gauges where the QA is being done, and it does the log flows rather than the total flows. It uses log flows for reporting purposes, and this shows, and for instance, this will show if there's a bias overall in the flow estimates, either high or low compared to what the gauge log 10 flow is. The standard error of the estimate is in %, and this would be, for instance, for the runoff step, this would say that roughly, you can interpret this as 2/3 of the flows are plus or minus 21% for the EROM flow estimates. And by the time you get to the plus flow AR, you're still at 21% plus or minus. It's difficult to come up with an absolute value for the final gauge flows because we use all the gauges. Okay, we do have a gauge sequestration process that's not really perfect and doesn't really work super well for doing a QA on the absolute best flow values, which are the QE. And the reason we can't do that, we're using all the gauges, so we would always come out perfect, you know, which, I mean, that would be fun to do, but, you know, it doesn't quite pass the laugh test. Okay, now the other thing is we produce our QA files, and this is really, essentially this was the input information used for doing the QA report, but it provides every place where we had a gauge, whether it was a reference gauge or not, the drainage area, and then the flows, and Q_E is the gauge flow, okay? So, you know, we're always perfect in that sense. So you can compare the Q_E to any of these other flows and to see if, you know, just to give you a handle, mapping them also is sometimes interesting for patterns. And it's a DBF. You can easily import it into Excel or whatever. And I've used it for QA. And this is pretty much what it looks like. This is in the Tennessee River Basin. And you see I've got a couple of outliers down here. I've looked at them and I haven't figured out quite why that's an outlier. I'm thinking maybe I'm in a karst area, but I can't guarantee that. And Tommy won't pay me to go visit the gauge, so I can't tell for sure. Anyway, It does, in general, it does pretty well, and the QA statistics in terms of standard errors between being, you know, plus or minus 20% is pretty darn good there. So that's the sort of thing you can do with that. Now, the second method I mentioned is the Vogel method. It's a log-log regression method, and it uses mean annual precipitation, mean annual temperature, bias correction factor, and drainage area. And so it, okay. Somewhere I lost my, I lost a little formatting on that. Anyway, it's a regression method developed by Professor Vogel. One of the things about the Vogel method, now EROM for all flow lines that have flow, okay, all flow lines, and coastal catchments, it produces flow estimates for all of those. Vogel will only work within the range, is only provided within the range of the data that that he used. He specified not to go out, not to extrapolate from his data. And so we have the data limits. And so there will be a lot of missing values in there because we do not extrapolate from his regressions. And so that's why in the Vogel and the mean annual flow and the mean annual velocities, we will get a lot of missing values because for the small streams and for larger streams, we will just have missing values. But for EROM, you'll have flow values on everything. Okay, now for velocities, we use a method developed by Harvey Jobson of USGS. It's actually a very, very nifty method. It's a multiple regression. It uses drainage area, which we have, which is one of the major plus parts of NHDPlus. And we have slope, which I explained earlier. We have stream flows, which I've just explained what we get. And it uses those to estimate a velocity. And there's also a method provided that does not require the slope. It can use the drainage area and the flow values and does not require slope. And we do have situations in our slope estimates where we have missing values for slope because we can't, any type of interpolation or whatever to get our slope values, we just have to put a missing value. It's not often, but we have to. So we use this other method in those cases for estimating slopes. By the way, in Appendix A, all of the nitty-gritty ways these things are done in excruciating detail can be found. Now, in calculating velocities, which are very important for estimating times of travel, in NHDPlus v1 and in the initial release of v2.1, we just did Jobson method was used for everything. Streams, lakes, estuaries, it was done everywhere. So, but that's not really particularly correct because, first of all, the Jobson method is really only for flowing waters. Okay, so right now, when you estimate velocities in EROM, right now, when we're in water bodies, we're in lakes, we've set the velocities to -9998, and we're setting an estuary flag. We're creating an estuary flag now, and then the velocities there will be set to -9999 because we don't know what kind of velocities to put in for estuaries. And times of travel, Rich Moore has developed a really neat thing for lakes, for estimating times of travel in lakes for mean annual flow. And it has to has to do with estimating the volumes of the lakes and such, and it's that we expect to be releasing pretty soon, going through some final reviews now, but it's going to be a very powerful tool when it is released, so keep track of the NHD release notes for that. So we're tightening this up and straightening this up so we're not putting the Jobson method willy-nilly everywhere. Again, like I said, it's only valid for flowing waters. And in those areas, it's simply length divided by velocity, and you can easily move upstream and downstream. Bill Samuels uses this in icy water a lot, and it's tended to work out okay. Tended to work pretty well in the flowing waters. Okay, now I'm going to switch gears. I'm going to talk about the VPU attribute data. And this is the data back behind the development of EROM and Vogel flow methods. For EROM, we need allocations, of course, of mean annual and mean monthly runoff, temperature and precipitation. For Vogel, needed accumulated values of drainage area, mean annual temperature and precipitation. And I'd like to note we used the divergence routed methods, which maintained flow balances throughout the system as we went. So we used the divergence methods. Now this data, I mentioned this before, it's built using the CA3T tool, which is one of the tools that's available on your on the NHDPlus website, and you can download it and you can operate that. I've talked about that a little bit. Now let me talk a little bit about how CA3T operates. Basically it starts with a grid, for instance, mean annual runoff. And the first thing it does is it allocates those values to catchments. So, and when it's allocating to catchments, this is the result. It's really a feature ID. Remember, the catchments have feature IDs. They don't have, I mean, you can generally easily relate them back to COM IDs, but they start out as feature IDs. So the result, for instance, here's the average value of the runoff for each catchment, and this would be what the results file would look like for runoff mean annual, and it comes back as a text file. And then it does the accumulations, and here it would do an accumulation for temperature of the mean temperature accumulating as it goes downstream. Now, we've talked about accumulations and how they relate to divergences. And here we're going downstream. Here's the minor path of a divergence. Here's the main path of a divergence. Okay, and what CA3T will do, when you do divergence routing, you're routing everything down the main path, and you're treating the minor path as a start reach. So what happens is then when, for instance, you're doing cumulative areas in CA3T, you would get, on this flow line, you would have the divergence drainage area square kilometer and the tote drainage area square kilometer would be the same, because that's the main path and everything works out nicely there. However, here on the minor path, the divergence routed value is 0.342, which is actually would just be the drainage area of the catchment for this particular minor path divergence, but the total is 2.0295, which is, you know, very similar to this one. So divergence routing and total routing will produce quite different results once you start getting into divergences. And again, the effects of the total versus divergence accumulations, they can carry downstream quite a bit, and it can make the total routing quite complex, and it's not for the faint of heart, but it's very powerful what CA3T does and what the what the routing is that the VAAs allow with the return div codes. And, you know, you get divergence upon divergence upon divergence, and these things just get more and more interesting as you keep going down, as Cindy was talking about. Now, another nice thing that CA3T will do is it will do your accumulations across your drainage areas. For instance, to get down to the lower Mississippi, here's the Tennessee, which flows into the Ohio, which flows into the lower Mississippi. You've got the upper Missouri into the lower Missouri, into the upper Mississippi, and into the lower Missouri. And then you've got 11 flowing into 8. And it will accumulate across those drainage areas, which is a very nice thing. Okay, the VPUAttributeExtension file, these are the files. We got the cumulative precipitation values for mean annual. We also have the middle latitude point for each catchment. That's actually used in the excess evapotranspiration step, so I wind up, but it could be useful just having sort of the midpoint latitude of every catchment. It could be useful for different things. I've found it handy at times. Then we get all of the allocation of all of the precipitation for mean annual and month, and for temperature for mean annual and month. And then we have the runoff allocations for mean annual and month. And so here are the extensions that I've talked about. I've talked about EROM, where in each VPU we have the month, we have the QA file, and we have the QA report and the QA files. We have the Vogel extension, and then in the VPUAttributeExtension, we have these different tables, and then we've also got the cumulative runoff has now been added to this particular extension. Finally, I'd like to say that there are other extensions that we have in NHDPlus. And remember what I said at the beginning, in NHDPlus land, extension means something that was made after the core processing. And so we've had some additional accumulation extensions done, which these are actually used for some of the tools, simplified catchment extension, and then NLCD 2011 extension. So, and other extensions can be added as time goes on. We haven't limited ourselves on those. And so that's where we are on stream flows and velocities and extensions in the NHDPlus version 2.1. Any questions? Yes, sir.
I always wanted to ask you this question, and I never have, but I'll do it today.
Thanks for doing it in public.
No, don't worry about this question.
I know.
How do you feel about Vogel flows versus EROM flows? How do they compare? When would you use one versus the other?
I tend to favor the EROM flows because I think that the 5-step process and the tuning, if you will, the gauges and such, makes them, I think it makes them better, if you will. The Vogel, they were really good for what they did and when they did it. But those regression equations are by hydrologic region, and they do have serious limits on their boundaries. So I like the 5-step process that we've gone through with the EROM. That's my personal opinion.
Thanks.